So next up, we have Minghao Yue sharing results of ALMA observations of sub-kiloparsec structure of the host galaxy of a redshift 6.5 lensed quasar.
All right, thank you.
Share your screen.
Yeah, let me share my screen. So, and start showing the slide. So great. Can you see the slide and can you hear me?
Yes.
Okay, perfect. Great. So can I start now? All right. So hello, everyone. This is Minghao Yue from the University of Arizona. I am a 5th-year grad student working with Professor Xiaohui Fan. And first, let me say thank you to the organizers to give me the opportunity to make this presentation. And today I'm going to talk about our recent studies of a truly unique and interesting object, which is a gravitationally lensed quasar at redshift 6.5. So this quasar, J0439, was discovered by our group a couple of years ago, and is so far the only known gravitationally lensed quasar beyond redshift 5. So here I'm showing the optical to near infrared spectrum and the HST images of J0439. We can see from the HST images that J0439 is clearly resolved into multiple components, including the foreground diffractor galaxy and the lensed images of the background quasar. So the best fit lensing model suggests a magnification of 51. Such a high magnification makes J0439 one of the brightest quasars at high redshift in all wavelengths. And lensing also allows us to reach a high spatial resolution on the source plane, making J0439 an ideal case study of high redshift quasar population. In this talk, I will focus on the recent ALMA observations of J0439. So the ALMA program contains 2 parts. The low resolution part, aiming at measuring the overall properties of the quasar host galaxy with high signal to noise ratio, has been finished in 2018. And the high resolution part will capture the small scale structures of the quasar host galaxy and has only been partially executed. Well, hopefully it can get finished after ALMA resumes operating. And this talk will focus on the low resolution data, and with a beam size of about 0.3 arcsecond, the lensed arc of the host galaxy is already clearly resolved in the low resolution ALMA image. We also extract the C+ line emission line of J0439, and it shows a regular Gaussian profile and an ordered rotation-like velocity field. According to the best fit lensing model, lensing magnification boosts the physical resolution on the source plane to about 0.8 kiloparsec, which is sufficient to well resolve the quasar host galaxy emission. So we fit the continuum and the integrated C+ emission line as Sersic profiles, and we find that both of them can be pretty well fitted by a Sersic profile with index around 1. In other words, the host galaxy of J0439 is basically an exponential disk. We also construct the source plane moments for J0439, and as you can see here, it clearly shows a rotation-like velocity field. These features suggest that J0439 is a rotating galaxy with a regular profile, and it's probably not an ongoing major merger. The reconstructed source plane moments actually reveals many interesting aspects of J0439. So the first point I want to discuss here is the C+ gas kinematics. Well, we can look closer at the source plane moment 1 map and the position velocity diagram. Again, both plots show features of a rotating system. For example, we can see the rotation curve on the PV plot. So with the rotation curve, we can estimate the dynamical mass of the host galaxy. I mean, one thing to notice is that the rotation curve itself cannot constrain the inclination angle of the rotation axis. So that's why we have a sin I term in our result. We also get the black hole mass from the near IR spectrum, with which we can estimate the black hole to host galaxy mass ratio. This ratio for J0439 is significantly, several times larger than indicated by local relations. And this so-called overmassive black hole phenomenon is quite common and well known in high-redshift quasars. There are many plausible scenarios for this, from an early supermassive black hole growth relative to their host galaxies, and some other people also suggest this is a pure selection effect. And here, a careful analysis of J0439 shows another possible reason for the overmassive black holes we see in high redshift quasars. So to illustrate this, we fit the C+ emission as a thin axisymmetric rotating disk. It turns out that a rotating thin disk model fails to describe the C+ emission in J0439. The main reason is that the velocity gradient, which I mark as the black line here in the plot, is not in the same direction as the flux major axis. In contrast, we can imagine a tilted thin disk model, where we'll expect that the two axes should have the same direction. We also go through the literature from which we find that many other high redshift quasars have similar misalignments, similar plots to J0439, which I'm showing here. So in other words, J0439 and probably many other high redshift quasars have a gas kinematics that is more complicated than a rotating thin disk. One consequence of this is that we'll have some significant systematics when estimating the dynamical mass. If we look at the moment-2 map of J0439, the velocity dispersion is about 80 kilometers per second. Such a high velocity dispersion will almost certainly lead to a thick geometry. Well, this could be the reason why a thin disk model doesn't work. And since the turbulence can support the galaxy against gravity, there will be an additional term in the dynamical mass estimation, as I'm highlighting here. So if we use only the rotation velocity to estimate dynamical mass, the result is likely underestimated. In other words, one possible explanation to the overmassive black holes we see in high redshift quasars is that we are indeed underestimating the host galaxy mass. The analysis of J0439 thus illustrates the need of a careful modeling of high Z quasar host galaxy dynamics to fully understand this question. In the case of J0439, we realize that the current data still doesn't have enough resolution for a detailed dynamical model, and the upcoming high-resolution data will provide more information. Another interesting point is that J0439 is an extreme star-forming system. We estimate the star formation rate using the far-infrared SED and measure the molecular gas mass using the CO emission lines. J0439 has a pretty high star formation rate, and correspondingly, it is very gas-rich. The gas mass fraction is estimated to have the order of unity. So we can compare these values to some theoretical limits. I listed two limits here. The first one is the Eddington limit of the star formation surface density, which corresponds to the maximum gas collapsing rate limited by the radiation from existing stars. The second one is the freefall limit, which is basically the gas collapsing rate corresponding to the freefall timescale. If we compare these two limits to the observed values, we'll find that they are pretty close to each other. In other words, J0439 is forming stars at the maximum possible rate. So that is what I mean by an extreme star-forming system. So we want to ask this question: what triggers the intensive star formation in J0439? Well, when talking about strong star formation, one obvious thing to consider is gas-rich major mergers. In the case of J0439, however, as we discussed earlier, it has a regular shape and a rotation-dominated velocity field. It's probably not an ongoing major merger. If the star formation is indeed triggered by a merging event, the only possibility would be that J0439 is the remnant of a recent merging event. To confirm this, we need to seek for signs of a recent merger, like irregularities in the host galaxy, and hopefully the upcoming high-resolution ALMA data will do this. And another possibility is strong cold gas inflows from the CGM. This is also a mechanism that has been proposed by simulations for a long time. Given the large gas reservoir in J0439 and with the help of lensing magnification, it will be a very interesting thing to look for cold gas streams around J0439 using deep imagings of, say, CO or C+ emission lines. And finally, let me talk more about the high-resolution data that is upcoming in probably the next year. As I mentioned earlier, the high-resolution part of the ALMA program has been partially executed, and here I'm showing the data that has already been collected by the program. With the high-resolution data, we will solve many of the remaining mysteries we mentioned in this talk. For example, we will build a better lensing model for J0439, and we'll perform detailed dynamical analysis of the host galaxy. I mean, to me, the most exciting thing is that the high-resolution data will resolve the sphere of influence of a central black hole, and this will allow us to measure the black hole mass directly using gas kinematics. And this is probably the first time that we can do such kind of experiment beyond the local universe. And I will put my summary here. Thank you for listening, and I will be happy to take questions.
Great. Thank you so much, Minghao. Let's wait a little while for folks to enter their questions on Slack.
Okay, that's just a first comment, at least on your talk, saying that combining the high and low resolution data might be very interesting. Are you planning to do that?
Yeah, actually, this plot I'm showing here is a combination of the two. I mean, the low resolution data basically samples the overall structure and gives us a higher signal to noise ratio. Yeah, so our plan is to analyze the visibility of both low and high resolution parts simultaneously when all the data is collected.
Mm-hmm.
Okay, we have another question. In the Milky Way, we see intense starbursts and elevated star formation rates, even due to minor mergers, like 100 to 1 in stellar mass ratio. Those minor mergers drive pre-existing gas into central starbursts. Could this be possible for this source?
Yeah, that's a great question. Actually, we consider minor mergers pretty likely. Let me go back to the best fit lensing model here. So here, I'm claiming that Sersic profile can describe the emission pretty well. I mean, but there's a little bit residual, which contributes to several percent of the flux. So that's why I say a Sersic profile works well. But you still see some residuals, which could indicate that there are some kind of small structures in the host galaxy. And we do consider minor mergers a very likely explanation to such kind of structures, and we'll definitely investigate more about that. And that's probably the task of the high resolution part of the program. And yeah, thank you for the comment. I think it's pretty, I mean, at least a very appealing scenario. Yeah, thanks.
Yeah, it'll be exciting to see that high resolution data in full for sure. So another question is, can differential magnification explain the misalignment between the major axis and the flux distribution and the rotation axis?
Well, I mean, well, it could be there could be some contributions to this issue. Say, if the overall shape of the host galaxy is I mean, so if there's some bar-like structure at the center and is highly magnified, and that will kind of dominate, say, if we fit a Sersic profile to the emission. So this kind of illustrates why we want a more detailed lensing model for this host galaxy. So that's for J0439. I think, yeah, differential magnification can play a role in this. And but regarding for the issue itself, I actually have I gathered something from the literature that we can see these are just normal quasar host galaxy at high redshift. So this, as I said, this misalignment is pretty common. I mean, if you go through these plots, I saw like 30 to 50% of them have some obvious misalignments. That depends on how you define obvious. But I mean, this is a pretty common phenomenon in high redshift quasars.
That's fascinating. Well, hopefully, so we're out of time. Maybe you can answer a few more questions over Slack, Minghao. Thank you very much for a great talk.